Pluto is a distant and confounding minor planet, once considered a part of our planetary group's family. However, recent alarming announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an amazing revelation. They suggested that this chilly world is on an impact course with Neptune. Yet, how could this happen? And what might be the results of such a significant event? Are we seeing an intriguing cosmic eccentricity, or is there something else to this approaching limitless effect? Join us as we investigate the conceivable outcomes of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet, is somewhat an enigma due to its odd orbit, and it remains a subject of interest and study in the astronomical community. According to recent projections by leading specialists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two bodies, which could represent a critical risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires an unbelievable 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. However, the interest doesn't stop there. Pluto's orbit is marked by its astoundingly curved shape, straying far from the almost round orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination of 17 degrees to the ecliptic plane. The course Pluto follows is much steeper compared to other planets. One of the most interesting parts of Pluto's orbit is its crossing point with Neptune's. For approximately 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, challenging what would expect from their positions in the planetary system. This prompts the natural question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. Shortly after Pluto's discovery, research into its orbit began. Initially, astronomers attempted to determine its unique orbit. Unlike other planets, whose orbits lie mostly close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and curved shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space involves figuring out how three bodies, like Pluto, Neptune, and the Sun, move and affect each other through their gravity. Pluto's orbit is, in fact, turbulent. Minor deviations in starting conditions can lead to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over especially long time scales, keeping tumult under control. Recent simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Jupiter's massive gravity is strong enough to keep Pluto on a stable path for potentially billions of years. In order to maintain celestial dynamics in order and consistency, these forces are necessary. Without them, our local planetary system would be a place of much more unrest and unpredictability. Pluto's orbit is a remarkable illustration of celestial mechanics at play, displaying both stability and chaos within our local planetary system. The unique characteristics of its orbit, shaped by the gravitational forces of nearby planets, especially Neptune, highlight the intricate and dynamic nature of space. Predicting major events, particularly when they involve turbulent orbits like Pluto's, presents tremendous challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. While numerical simulations offer a powerful means of understanding and predicting the future behavior of celestial bodies, they also highlight the limitations of our predictive abilities. So, why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in astronomy, have expressed concern about a possible collision between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a captivating and devastating event in our neighborhood planetary system. The impact would release an immense amount of energy, probably breaking Pluto, given its smaller size and icy composition. Debris from the collision could scatter across the planetary system, potentially posing danger to other planets and their moons. For Neptune, such a collision could alter its current atmosphere and possibly its orbit, depending on the specifics of the crash. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings a unique perspective to the discussion as well. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics offer valuable insights into the mysteries of major phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital elements of celestial bodies like Pluto can yield important insights for future space missions. This knowledge can help in navigating the planetary system more efficiently, predicting potential hazards, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. Regarding the physics of planets, celestial mechanics and theoretical physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that could potentially connect with string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, aims to explain the fundamental forces and matter in the universe. The collision may result in extreme energy and gravity conditions, possibly allowing string theory's predictions to become observable. For example, the high-energy impact could provide insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. While the direct effect on Earth would be negligible due to our distance from the outer planetary system, the scientific implications of such an event could be profound, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's confounding dance around the Sun continues to enrapture scientists and enthusiasts alike, offering a window into the complexities of celestial mechanics. While its reclassification as a dwarf planet sparked discussion and redefined our understanding of planetary bodies, recent discoveries about its orbit have reignited interest in its role within the local planetary system. This orbital intersection is safeguarded by a phenomenon known as orbital resonance. Specifically, Pluto and Neptune are locked in a 3:2 orbital resonance, meaning that for every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This resonance ensures that despite their paths crossing, the two bodies never occupy the same space at the same time. It's a cosmic choreography that has preserved their delicate balance for millions of years. Nevertheless, the idea of this resonance being disrupted, whether by external gravitational forces, a rogue object, or internal instabilities, remains a point of concern for some astrophysicists. In such a scenario, the stable harmony that has long protected these celestial bodies could be thrown into chaos, potentially allowing for a future collision. Critics argue that the chances of such an event occurring are infinitesimally small. Pluto's orbit is not only highly inclined but also carefully orchestrated by the gravitational influences of the solar system's gas giants, especially Jupiter and Saturn. These gravitational giants exert a shepherding effect, helping maintain orbital order across the solar system. Furthermore, advanced computer simulations accounting for billions of years of celestial evolution consistently show that Pluto and Neptune's orbits avoid direct collision. So, why the sudden alarm? Some suggest that the statements made by Tyson and Koku are meant not to incite panic but to ignite curiosity in scientific debate. By exploring extreme but plausible scenarios, they encourage further investigation into the dynamic behavior of our solar system and the limits of orbital stability. It's a reminder that even long-established cosmic truths deserve ongoing scrutiny in the light of evolving data and improved modeling techniques. The broader implication is clear: celestial mechanics is not static. It's an ever-changing field where slight shifts in initial conditions can lead to vastly different outcomes, an idea central to chaos theory. The future paths of celestial bodies like Pluto remain bound to an intricate network of gravitational pulls, resonances, and historical interactions, making them rich subjects for theoretical physics and astronomy alike. Moreover, as humanity begins to plan deeper forays into outer space, understanding the long-term stability of distant orbits becomes increasingly relevant. Whether for robotic exploration, future colonization prospects, or planetary defense strategies, we must fully grasp the nuances of celestial motion. Pluto's peculiar path offers a case study in how even seemingly minor planets play essential roles in the broader architecture of the solar system. As of now, no credible scientific model supports the idea of an imminent Pluto-Neptune collision. However, the attention it has drawn underscores the wonder and complexity of space science. It serves as a compelling example of how theoretical scenarios, no matter how unlikely, can help us better understand the universe and prepare for a future among the stars. In the end, Pluto's eccentric orbit and mysterious past continue to inspire questions that stretch across disciplines, from astronomy and physics to philosophy and space exploration. Whether it ever meets Neptune in a dramatic celestial event or quietly continues its frozen journey at the edge of our solar system, Pluto will remain a symbol of cosmic mystery and the boundless reach of human curiosity. Neptune's orbit, at points during its long journey around the Sun, plays a crucial role in shaping Pluto's path. The gravitational influence of other planets, particularly Neptune, has a significant impact on maintaining Pluto's orbital stability over hundreds of years. Despite the turbulent nature of its path, numerical simulations and theoretical models are essential for predicting the future behaviors of celestial bodies and for understanding the complex interactions between planets. Even though Pluto's orbit has been erratic for thousands of years, these simulations show that it has remained relatively stable within the larger framework of the solar system's gravitational field. The potential for a collision between Pluto and Neptune, as proposed by astrophysicists Neil deGrasse Tyson and Miyoku, highlights the ongoing uncertainties and intricacies of planetary dynamics. While such an event remains hypothetical and highly unlikely in the near term, the gravitational dance between Pluto and Neptune underscores the fragile balance of forces that govern celestial bodies within our solar system. Beyond its scientific significance, the study of Pluto offers practical insights for future space exploration missions. The New Horizons spacecraft, launched by NASA in 2006, provided exceptional images and data of Pluto and its moons during its historic flyby in 2015. The mission revealed stunning details of Pluto's surface features, including mountains of water ice and vast fields of frozen nitrogen, enhancing our understanding of the geological processes shaping this distant dwarf planet. The success of the New Horizons mission highlighted the technological advancements and collaborative efforts required for deep space exploration. By studying Pluto and its moons, scientists gained valuable insights into the diversity of celestial bodies and the environmental conditions present in the outer regions of the solar system. These discoveries have implications for future missions to explore other dwarf planets and trans-Neptunian objects, furthering our understanding of planetary formation and evolution. Additionally, debates regarding the criteria used to classify celestial bodies within the solar system have arisen due to Pluto's designation as a dwarf planet. The debate over planetary classification reflects broader questions about scientific classification systems and the evolving nature of astronomical knowledge. While Pluto meets some criteria for planetary status, such as orbiting the Sun and having sufficient mass for self-gravity, its classification as a dwarf planet highlights the diversity of celestial bodies beyond the traditional 8 planets. Studying Pluto's orbit expands our knowledge of celestial mechanics and planetary dynamics in the outer reaches of the solar system. By examining the interactions between Pluto, Neptune, and other celestial bodies, scientists can gain further insights into the formation and evolution of planetary systems. These insights are crucial for developing theories about the origins of our solar system and for understanding the processes that shape planetary bodies over billions of years. Pluto's discovery and subsequent study have contributed to our understanding of planetary migration and the formation of the Kuiper Belt, a region beyond Neptune populated by small icy bodies. Studying Pluto's orbit provides clues about the gravitational interactions that may have influenced the formation of planets during the early stages of the solar system. The gravitational influence of Neptune on Pluto's orbit offers an example of how interactions between different planets can shape the trajectories of smaller bodies over time. Future research on Pluto's orbit and the potential for a collision with Neptune could help refine our understanding of planetary dynamics and improve our predictions about the behavior of celestial bodies. As we continue to explore the mysteries of Pluto and the outer reaches of the solar system, we may uncover new insights into the fundamental forces that govern our universe. The collision of Pluto and Neptune, though unlikely, would be a monumental event that could provide invaluable opportunities for scientific discovery. Whether or not it happens, the investigation of Pluto's orbit and its relationship with Neptune will continue to inspire astronomers and physicists as they strive to unlock the secrets of our cosmic neighborhood. Moreover, the study of Pluto and its interactions within the Kuiper Belt has reignited interest in other distant celestial bodies that were once considered too remote or insignificant to warrant attention. Objects like Eris, Haumea, and Makemake, also classified as dwarf planets, offer further opportunities to study variations in composition, orbit, and geological activity across the outer solar system. These bodies, along with Pluto, serve as time capsules, preserving information about the early solar system that has long since been altered or lost in the inner planets due to geological and atmospheric processes. Technological advancements in telescope design, data analysis, and artificial intelligence now enable astronomers to model complex gravitational relationships with greater accuracy and efficiency. These tools allow scientists to simulate millions of years of orbital evolution, revealing possible resonances, instabilities, and transitions that shape the dynamic architecture of our solar system. With these capabilities, researchers can better predict how planetary orbits may shift over time due to subtle interactions, including those involving small, seemingly inconsequential objects like Pluto. At the same time, the philosophical implications of redefining what constitutes a planet challenge us to reflect on the nature of discovery and the frameworks through which we interpret the universe. The reclassification of Pluto sparked passionate responses not only from the scientific community but also from the public, underscoring the deep cultural and emotional connection humans have with space exploration. For many, Pluto's demotion served as a reminder that scientific understanding is not static, it evolves with evidence, inquiry, and debate. In educational settings, Pluto continues to serve as a compelling case study. Teachers and students use its story to explore scientific methodology, the importance of definitions, and the balance between tradition and progress in science. The dialogue surrounding Pluto helps to foster critical thinking and encourages curiosity, qualities essential to the next generation of astronomers, physicists, and explorers. Looking ahead, missions like the proposed Pluto orbiter and potential Kuiper belt surveys promise to deepen our knowledge of this enigmatic region. These endeavors could provide detailed maps of Pluto's atmosphere, long-term weather patterns, and internal structure. By expanding our understanding of such distant worlds, we inch closer to answering larger questions about habitability, planetary systems beyond our own, and the conditions necessary for life. Ultimately, Pluto's journey, from discovery to planetary status, and from demotion to renewed scientific relevance, mirrors our own evolving quest to understand the cosmos. It stands not as an outlier, but as a symbol of how exploration continually reshapes our view of the universe. The story of Pluto, far from being over, is still being written, with each discovery propelling us further into the vast and mysterious frontier that lies beyond Neptune.